Okay, thanks everybody. Thanks for joining. I'm Fabio. I work at Hopsworks. And so today we're going to be talking about how to build a serverless electricity price prediction with Python, Hopsworks, and a bunch of other services. So as you can probably hear from my accent, I'm not from the States. I'm actually Italian. And we kind of have a situation in Europe right now. Kind of electricity prices are kind of to the moon. So like the idea behind it is basically just to kind of build a model to predict these prices and try to, in the meantime, try to kind of look at the workflow and look at how the pipelines work together and how to optimize that. The system is quite interconnected to each other. I don't have access to like real quality data, so there's a bunch of like open data set you can use. I'm going to be focusing only on the Swedish area. Sweden is divided into what they call 4 different bidding areas. So they are independent kind of market, and then electricity flows between the different markets. And obviously it's interconnected with the rest of Europe. In this specific talk, we're going to just focusing on the bidding area number 3, which is the Stockholm region. Only because kind of I live there, so that's what I'm interested on. And the other aspect is that obviously because it's connected, like electricity prices in, I don't know, for instance, in Germany affect also how the electricity pricing in Sweden actually gets priced. The nice thing about Sweden is that the energy mix, so the way energy is actually generated, it's not really reliant on natural gas. So we can ignore pretty much a lot of news out there and just focus on like smaller and more simple features to kind of manage. And so that allows us to focus more on the workflow and the pipeline and how to optimize that. Okay, so as I mentioned, we want to make sure that we have a good model, but with a subset of features. So we're going to be looking at the weather data. I don't know if you've ever been in Sweden, but it's quite like gloomy, especially during the winter. There is no really a lot of sunlight. Obviously, has effect on terms of like if you have solar power generation and so on and so forth, and also in terms of consumption. We're going to be looking at a bunch of features coming from how the data was how the power was generated. You're going to be looking at how the power is exchanged between different flows, different regions, and also looking at the calendar year. Obviously, holidays and like weekends, the power generation consumption is lower. So if you take a traditional model and architecture, well, the way you will set it up is basically you have all your data sources, you have your pipelines taking data from data sources and feeding into the model, and then the model is built. There are, I would say, 2 problems here. The first one is obviously we want to make an inference at the end. We want to be able to use this one. And to be able to use this model, we need the historical data that is available in your data sources. So what was the weather in the past couple of days? Obviously, as effect, even at inference time. And the other aspect is that all these pipelines going from data sources to your model are somewhat connected to the model. But you could potentially have a bunch of different models, and you might want to reuse all those features. So you want to also disconnect the data sources and pipelines from the model itself, right? So how do we do that? The basic idea here is to kind of split up the single pipeline, the single workflow into multiple pipelines, right? The first one is basically picking up data from data sources and creating features. The output of that pipeline is actually the feature store. And the feature store in that case acts as a shared buffer between different pipeline or like computer bus, for instance. These are obviously executed can be executed in batch. In our case, it gets executed nightly. That's when data is available. It can be a streaming sources, so that pipeline can also be a streaming. And the different pipelines, different from here, different pipelines can be independent from each other. So you might have a pipeline looking at the weather data and creating features out of the weather data, can be independent from the one that creates features out of the power generation mix, essentially. The next step is obviously taking data from the feature store and creating a model that's what the training pipeline comes into the picture. And again, the output is again put into the bus as a form of model, right? So now the model and the features are available in the feature store. And finally, we get the inference pipeline that uses the model, uses historical data, and potentially uses the input data to make predictions. So this is kind of the high-level architecture. And if we were to kind of separate the different components and building blocks for this one, we have a section up there which is basically the compute section, where all the computation for both the feature pipeline and model training actually happens. We have a state at the bottom. It's basically all your feature data and your model. And then we have some more compute on the top right for doing inference. And the way we want to address this problem is that for compute, you're pretty much flexible to use whatever stack you want to use. There's a ton of options out there. In my case, I'm just going to be using a bunch of Jupyter notebooks, and I'm going to be using GitHub Action for scheduling. But there are a lot of tools out there that you can use for either scheduling, but also just run the PyData stack to basically create features and so on. Obviously, we want to focus on the state part. Then nobody wants to really manage state. It's quite cumbersome. That's where kind of Hopsworks comes into the picture to help out there. So the new pipeline looks something like this. We have always the sources. You have their collapse. You get your compute layer computing both features and models, so training actual model and saving them into the state, which is the state manager, which is Hopsworks. And in this specific case, for this specific pipeline, we're going to be seeing data. We also create predictions and store them into the feature store. We're not going to do that real time, but we pre-compute them and make them available in Streamlit, which is going to be our UI to display the outcome of the predictions. And again, if you look this same architecture before, compute layer, state layer, again the final compute layer for the inference. Okay, so the part that we want to focus most is actually the state management. So we're going to look at the feature store aspect. The feature store aspect, as the Hopsworks feature store, has two main API to interact with. As an API to write into the feature store, and as an API to read from the feature store. The way it works, and I'm going to show you in 1 second. Let me open a notebook. Oops. Is the following. So if I look at, this is one of the pipelines that actually generates the features for the power mix. Essentially, just reading a bunch of CSV files, and that's how the provider makes them available. We're going to be dropping a bunch of features, a bunch of columns which are not going to be used. They are not available in the region specific. We're going to just do some column name manipulation, fixing the time format. This is really important. Later on, we'll see how we deal with times and features created at different times. And then we're just going to fix the types for the different power sources. And eventually end up with data frame look like this. This is a Pandas data frame. You have all your features vertically, and then horizontally you have for each hour, you have the different power sources in megawatts essentially. And as you can see here, I'm not doing any normalization of features. You have pretty high values, pretty spread out values. And I'll come back later on why I'm going to write this as features. I'm not going to apply any transformation at this stage. And then this is where kind of the Hopsworks API comes into the picture. I'm going to create a feature group. So essentially, it's a set of features just with a bunch of metadata like name, version, if you have descriptions, the event time, and I'll cover later why it's needed. If I want to store it online or offline, and I want to also compute statistics for it. And then eventually, everything that is needed essentially take your data frame and call the insert method to write into the feature store. The way it's going to get written is by using this type of architecture essentially. So the data is going to land in a Kafka topic that Hopsworks manages, and then the data is get picked up from there and it's going to get written both offline and online in case you need it. Like you need online if you are doing real-time operations and real-time predictions. Offline is mostly used for training models, but also for if you're doing batch predictions. That's something you can use the offline feature store for. And the way then you can see that in the Hopsworks UI, you basically see all your features that you can have. You will see where things are being used, and I'll cover in a second the expectation part. And then you get a bunch of metadata that you can customize. You can also be looking at different statistics that are computed automatically, different power sources, both in terms of like descriptive statistics, but also in terms of like histograms, but also correlations between the different power sources that the Stockholm region uses essentially. Okay, so this is your feature group. We have many more of them. We have, I think, 5 or 6 of them. This is what I was mentioning before. So the holidays and the calendar features, power generation is the one we're looking at. How the electricity flows between different regions, and looking at the weather as well. And finally, we have this stores only labels, which is actually the day ahead price. So the price that electricity estimate for tomorrow at 4 in the afternoon or any other time essentially. So this feature group it just contains my my labels essentially. Okay. So the next steps is obviously creating a model out of it. Let me jump back into SlideShare. We're going to be using the second API. As I mentioned earlier, this was what it looked like before. So now we've broken down into multiple pipelines. Those pipelines are independent from each other. They can run at different times depending on when the data source is available. And what this creates, it creates a problem in terms of like creating a trained data set that is somewhat aligned or that is correct in time. And if I look at subset of the problem, I'm going to just take 2 features, and then this can be expanded to the entire data set. So I have the weather features in terms of like cloud coverage, and I want to see my label in this case for this specific subset of the model is going to be the solar output, right? The pipelines run independently, and they generate events at different times. So, for instance, I have 10:30, 11:30, and 12 for the weather feature group, and on this other side, I have at 11, 12, and 13, and 1 p.m. When I'm joining the features, I want to make sure that my label feature group gets matched to the most recent features that I have available on the weather feature group, right? So, if you look down at the bottom, the 4 megawatts gets matched with the event at 10:30. So basically the 87% of cloud coverage. And the 5 watts for 12 and 1 p.m. gets matched with the 12 cloud coverage, which is 82%, right? So this is basically allows us to make sure that even if the features are generated at different rates and at different times, when you join them together, you are joining them in a point correct time, in a point correct fashion. The way you would do it in SQL is through this massive query. It's quite like, it doesn't even fit on a slide, so it's quite like not clear. But this only covers the 2 features that we were looking at before, right? So actually the label and a single feature coming from 2 different feature groups. My model has a bunch more features coming from 5 different feature groups, so this query will be much more significant and much more cumbersome to write. The way we simplify that in the API is by actually providing a Python, a Pandas-like API, which allows us to basically say, okay, I want to select that feature from that specific feature group, and I want to select the mean cloud percentage from the weather feature group and join them together, and the API will automatically create the correct query and execute the correct query. And I can show you in the notebook. So if I go into my second notebook, you can see here, I'm going to select a bunch of feature groups, which are my group of features. I'm going to join them together, starting from my label feature groups. and I'm going to join them with the rest of the feature groups, and I'm going to exclude some of the features that either are not needed or they create problems and so on. So this is basically generate a query object. Ignore for a second this one. I'll come back in a second later, and create what we call a feature view, which is our read API, where basically say give the name, I give it the query that I want to use, the label, so what I'm trying to predict with this specific feature view, and I come back later on transformation functions. Feature view, imagine, are essentially a container for features that your model needs, right? They don't contain any specific data. The data comes in the trained data set. And the nice part about this API is that it allows us to generate multiple trained data set starting from the same feature view. So you basically have like the schema in the feature view for that specific model, and then as new data comes into the picture, like it just gets generated, you can recreate additional trained data set and retrain your model over and over and over, and you are guaranteed that the schema doesn't change. So you can just like automate that part essentially. But when you do that, this can create a bunch of problems in terms of training and semi-skews, because when you create additional trained data set, obviously the statistics of that trained data set changes, and so you have to be careful about what you're doing in terms of like transformation function, normalizations, and stuff like this. So the way we solve this problem in Hopsworks is actually by taking care of transformation functions. So when I register a feature view, I assign some transformation functions, and some of them come out of the box. So like min-max scalar, standard scalar, label encoder, all these come out of the box from Hopsworks. But like if you have your own, you can put your own there as well. And some transformation functions get applied in all cases. So when I generate a data set, when I am getting a feature vector for real-time inference, but also when I'm getting a batch data set for batch prediction essentially. And if you go back to my feature view generation, this is what these blocks actually represent. So for each of the features that I'm going to be using, I'm going to assign a specific transformation function, and then I'm going to register that transformation function with the feature view that I just created essentially. And then from there on, every time I do an action on that feature view, that those transformation function will automatically be applied. So I don't have to take care of like statistics for the trained data set and normalization and so on and so forth. Everything is hidden via the API for us. And so that's what happens here. Essentially, the next step is basically creating a bunch of trained data set for different subset of window. So you can specify the start, stop date for the data inside. And same thing happens, if you keep creating new trained data set version essentially. And those are also registered in the feature store, so you can track them in the UI as well. And you can see a bunch of information about where it comes from, all the different versions that you have generated, and trained data set that you have generated, and so on and so forth. So we covered transformation function. And the last thing I want to cover is about data validation, right? So one of the aspects we want to make sure that when you're using Hopsworks is it allows you to basically say leverage the entire Python ecosystem that's already available, right? One of the things you want to make sure, because the features are being shared across different projects, across different teams, you want to make sure that the feature data is actually valid and it's actually high quality. So the way you can do that in Hopsworks is by using Great Expectation, which is a pretty popular library for doing data validation. And the way you can do that is, let me show you the notebook for that. The way you can do that essentially is the following. So I have created an expectation suite in Great Expectation. You can basically specify, for instance, okay, the nuclear power generation cannot be negative. Same thing for solar. And I'm going to attach this expectation suite to my feature group, right? So when I do that, every time I write some data into the feature store, this expectation suite is automatically run against my data, my incoming data. And if the data doesn't respect the expectation suite, then the write is rejected. And that's what happens here. So I'm going to take a subset of data frame, and I'm going to just change the number to be negative. I'm going to try to write into the feature group again, and then this is basically going to say I'm not going to do that. The expectation suite fails, and like the write is rejected, and so I don't have that data into the feature group. But what I do have is a report that says your data has been like you're trying to write some data, and your data was rejected. So you can see it down here. You can see that at this time, this morning, I tried to write something, and the expectation suite was failing, and it got rejected. You can also configure the feature group in a way that it just checks, but lets it write through. So you can change the configuration type from strict to always, and if the expectation fails, you can still write it in. So that's what happens here. Essentially, it allows you to write even though the expectation was not complete successfully. So that's done at the beginning. Yeah. No, a good expectation is independent, right? And the thing is that you just basically attach the expectation suite directly into the Hopsworks, plug it in directly into Hopsworks. So some of our users actually already come with a bunch of expectation suites. They don't want to go through and write them. You just take them and say, okay, this is what I want my data to look like. And if it doesn't look like this, don't write it into the feature store. So yeah. Okay. Go back to the slides. And yeah, again, this is basically the same in slide format. And again, you can check that. You can check that in the example as well. So the final aspect is actually looking at the prediction service itself. What we want to make sure is that the data, like that once in every day or like once every hour, the new data is generated and new data is being returned to the being passed to the model, and some predictions are actually generated and registered with the feature store. So again, this is the same aspect. So this is we are at the end of the pipeline this stage. We're going to use the feature store again. This time you're not going to store features, but we are going to be storing actual predictions. So in the API, let me just 1 second. In the API, so this was the model training aspect. So these are different notebooks. You basically get your feature view again, and you have already generated trained data. So you basically just retrieve that trained data in a Pandas data frame, and then you send it through the model essentially. This is a TensorFlow model, and then you at the end basically store that model. In this case, you store it into Hopsworks, but again, there are a bunch of other tools that allows you to store the model into essentially. Yeah, so the final aspect is actually using this model to create predictions. So we have like a job in the background that basically populates predictions and actually uploads them as features in the feature store. So every hour there is a new prediction coming in. As you can see here, we have like a green button here, allows you to basically say these are available online. So you can have like web applications actually doing that, and we can have a look at them. So every time for every hour going forward, we have the price predicted stored into the online feature store. And what we can do is actually we can create a Streamlit application that basically set up the connection to the feature store, retrieves that connection to retrieves the feature group from Hopsworks and reads the content of the online feature store, and then uses Streamlit to actually generates like a web application, right? So you can go back to Hopsworks, go back here, and basically just show like just a simple graph. Streamlit is a nice package, allows you to do all sorts of graph and visualization using just pure Python code. So you can plug it in. You can plug it in the Hopsworks API directly with Streamlit and basically get out all sort of nice graphs and so on. Okay. slide. Yeah. So Hopsworks is available as a serverless platform, so you don't have to actually deploy anything. You can go on upload Hopsworks API and register for free. You get a bunch of quota. You can basically start interacting directly with the API, both for managing the features, but also for serving the model that we didn't cover in this presentation today, to serve the model in real time through a platform called KServe. So the two are integrated, and yeah, it's available. It's available for free essentially. There is another course going on that we are managing to kind of like cover these topics and a bunch more that allows you to kind of learn about the interaction of the with Hopsworks and the serverless ecosystem. That's it. Thank you very much. And I guess now, if you have any questions.
All right. Thank you, Fabio. Do we have any questions? Right.
Hey, thanks for the talk. It was really informative. Just going back to the very first slide, I guess, looking at the data sources, which ones are important, like the most important?
For Sweden specifically, the weather. The weather is kind of like allowed, because like most of the sources come from, like most of the energy comes from like hydroelectric power. So the way, like depending on like the how like the rainy the season was and so on and so forth, you have more or less capacity there. But also in terms of like cloud coverage and like how cold it was, a lot of the houses in Sweden are heated through electricity, not with gas. So obviously that has effect into the model itself.
Okay, thanks. I have another question too. So I saw at the end there you used a LSTM model. Have you tried Boost Trees? Do you want to talk about the difference you saw between them?
No, I just said yes. LSTM model. I didn't make any comparison.
Okay.
At that level.
Any other questions?
Hi. Also, thank you for the talk. So I've heard about Hopsworks, and so far as Feature Store, I hadn't really kept up in terms of like feature releases and things like that. So I wasn't aware of model registry as part of its offering. Can you speak to that a little bit more insofar as what sort of features are available, and how data scientists and also on the other side of it, ML engineers can interact with that?
Yeah. So the basic idea of adding the model registry and model server into Hopsworks was just to make it so that it's really well integrated with the feature store, right? So we put a specific effort into making sure that like when you're serving a model, all the connections to the online feature store, all the data sources from the online feature store are actually well connected. We didn't invent the wheel there. We just underline we're using KServe. So that's a pretty that was the old I don't remember the name. The old cave serving, like it's the old. It's a new name for the cave serving. For the the old name is called cave serving. For the serving platform on top of Kubernetes. The API looks something similar to. We're trying to mimic a lot what the community already is using for MLflow. So the way you actually register features, the register model, and so on and so forth. We're trying to obviously mimic that so that users don't have to come up with a completely new new patterns and so on and so forth. And that's about it, I think. I can give you a demo later on if you come up to the booth. We can have a look together.
Any other questions?
Yeah. So the question, do I have to repeat the question? Yes.
The question was, can the timestamp safe join be turned off?
Yeah. So when you create a feature group, you can basically avoid setting this parameter here, and that allows you to basically just the Hopsworks doesn't know like what is the time of the events coming in, and so you won't generate that specific thing. The time-based join, the point time correct join, it's a little bit more expensive operation because obviously you have to look at different groups on the other feature groups, but ensures a more correct data set. But if you wanna just disable, you can avoid setting that parameter.
I have one question. This looks like a online or like mixed batch streaming case. Do you recommend also putting features in the feature store when you're still in offline experimentation phase?
Yeah. I think there are two reasons for that. The first one is you usually don't work like alone, right? You're always collaborating with a bunch of different people, right? And so that allows you to basically share that work with other people. The other aspect is that there are a bunch of features that we didn't cover here. For instance, to do time travel or like look at updates and upserts. So even though you might have like a normal like a patch non-real-time use case, you can still benefit from a bunch of those capabilities to look back at what was the data maybe 6 months ago, or look at statistics and stuff